Assalamualaikum and very good night or day. I hope this will be a good time to review, prepare, or revise for the mechanical system design and MCU 5923. So let me share my screen. So this will be a revision of what we have learned last week. So I'm just going to focus on things that is included in the first assignment, homework 1, as well as what would probably be covered for the final exam, for the test for this course, which will be in a few weeks from now. Um, so it's probably nothing extra, nothing much new. But first of all, let's go back to this problem that we have encountered together in the class. So here we need to conduct a velocity analysis. So actually the stages in solving, we have to solve for or do a position analysis first for this linkage mechanism. And then after you're done with the position analysis, you got some of the unknowns. In this case, the unknown will be here. This is theta 3 and also theta 4. So in the position analysis, you will solve for this thing. Okay, so in this case, this is already given, so it should make your life easier. Okay, I know a lot of you guys want an easy life, but you need to know that things are not given to us very easily. Most of the time, we have to solve for each of the things according to its stages. All right, so in this case, we are given this information as well, the BB, which is the input link. And from there, actually, we can find what the omega is, because you know that V is equal to omega. So if you want to find omega, we can find that V over R will be omega. So we need to find what is the omega that causes this thing to rotate this way, or to the linear velocity to be in this way. The omega was rotate in this fashion, counterclockwise. So in the first loop, in this problem, so you focus on the inner loop or the main loop, which is made from this four-bar mechanism. You have the extension over there, you get to X, but don't worry about that first, because in order to solve for a lot of things, such as theta 6, you're going to need theta 3. So that is actually not known yet, but in the graphical solution here is already given. Actually, you can do with AutoCAD and get this very, very easily. All right, so here you have from A to C, you go R2 plus R3, and you'll get from A to C. Or you can take another route, R1 plus R4, and that will also get you from A to C. Okay, so from this relationship, this is the loop equation for the vector loop equation. And then you can expand each of them. So each of these R vector will give you in this form. You can break it into this form, except for R1. R1 is just a straight line to the right. So that can be shown in this manner instead. So if you got it in this form, I guess it's better to use this form, which is more simple, the simplest form, I would say. Okay, and then you have R2 is 15, the information from the question. 15, and the angle is, input angle at the moment is 130. So cosine is up, top portion, and the bottom portion is sine. Then for R3, you have 70. So theta 3 is not known yet, but theta 3 will be in the form of cosine and also sine. Then R1, we get 65 only in the x direction. And then R4 is 50, and theta 4 is not known. So these are the two unknowns. So if you break it up into top portion and the bottom portion, you can get two equations, scalar equations. But from there, we also have four unknown because our theta 3 and theta 4 are in cosine and over sine for each of them. And that will practically give us four unknown with two equations. So we cannot solve this very easily. So one way to solve this is to bring everything that we do not know on the left side, such as this one, and everything that we know completely on the right side. And we'll notice actually this is giving us this line. So this is R1 and this is R2. So R1 minus R2. So R1 minus R2 is actually giving us a line that goes from B to D, from B to D. So in this case, we are going to call this R5, big 5 over there, so small subscript. And then just plug in the numbers and get 74.64 and negative 11.49. That makes sense. 74 the right and then down by 11.49. Then we can find what is the scalar length for R5. So just take these components, get the root sum square, and we get 75.52, which is exactly was not shown here. I guess another you can draw that and measure this length to be 75.52. So this is correct. And then we have theta 5, which is here. We put the delta y on top, and delta x on the bottom. And since delta x is not a negative number, so we do not have to plus or minus 180. So it's just this one, and we got a negative 8.75, which is a small angle here. So that makes sense. Okay, that looks like it is correct. Then we have to look at this triangle. I guess it's between B, D, and also C. But this will be point B, D, and also C. Okay, B, D, C. Okay, so here we have R5, R3, and R4. We can get this value and angle between BC and also BD. So that angle, I don't know what this thing is called, phi or something like that. Or phi, I say. Phi. Yeah, to look up on the Greek letters. So here we use the cosine law and make sure the part that is opposite to this angle that you want to solve for is going to be in the negative portion here. So which is R4, so R4 square. So that will be, and then the other part that is on the side of the angle that you want to solve for will be 3 and 5. So just plug in the numbers and we got about 40 degrees. For 40 degrees, so we know now theta 3, we get to theta 3 from theta 5, we have to plus this angle phi, and then only we get to the R3, and that should give us the theta 3. So just take theta 5 plus phi, and then this will give us about 31.25. Okay, that is solved. I guess that is correct. Okay, now from the scalar part, we get back to vectors. So back to this equation, I guess from over here. So this is R3 and R4, and that is actually equals to R5. So R3 minus R4 gives you R5. So rearrange. Now that we actually have solved for R3, the only thing that we do not know is R4 completely. So just plug in the numbers here. 70 cosine 31.25, sine 31.25, which is from here. And then we got the R5 we calculated later, before, earlier. And this should give us negative 14.8 and 47.8. So that will be R4, so negative 14.8 and then go up 47.8. So that makes sense. And to do the calculation for the angle, so 14.8 will be down bottom here, and it is negative, so you have to add 180. So that gives us 107.2 degrees for theta 4, which is correct. Then we have you have to use, if you want to get to point X, you can find angle rho. So rho, again, this case, rho is between R3 and R6, and then it is opposite to R7. R7 will be in the negative part, R7 square, and plug in those values, and that gives us 44.41 degrees. And we can calculate, since we know theta 3, and just add this rho, and we get this theta 6, which is going to give us 75.66. So now from A, assuming A is 0, 0, we can get to X by R2 and R6 plus R6. R2 plus R6, which is going to be, then just plug in the numbers. We just solve for theta 6. So that allows us to get 0.26 and 50.24. And if you use AutoCAD or any other CAD, you get you can verify that this is correct, almost correct, right? I don't know which one is. I guess in this calculation, a lot of errors a little bit because we take maybe just 2 decimal points. Maybe that will contribute to some errors. All right, after we are done with all the position analysis, we can proceed to the velocity analysis. So actually from here, we differentiate with respect to time. So differentiate with respect to time, we get velocity. So interestingly, you see we maintain R2, and then we differentiate the cosine. Initially was cosine theta 2. So cosine theta 2, when we differentiate, it becomes negative sine. And the sine down here, differentiate becomes cosine. So we need to understand this thing. And then you have to differentiate the theta inside here. And that gives us this omega, or actually this is also theta dot. Okay, in other books, maybe they use theta dot. Okay, CO dot for velocity. Dot. But I guess I like to use omega instead, because how I was trained. And so we do the same thing for V3, expand, and we got this thing. And for V1, because V1 is based on R1, so R1 is fixed actually. This 65 is not going to, and also 0 is not going to change. So if something is not changing after some time, so it means it is the velocity for something that doesn't move. So if it doesn't change, means it is fixed there. So the velocity of something that is fixed is 0. Yeah, I guess that makes sense. So and then for V4, it is rotating. Link number 4 is rotating, so we are going to get something here like omega 4. Right, so once you do this, you can plug in the numbers of things that you already know, and you will see that only omega 3 and omega 4 are the 2 unknowns. So you can bring everything with omega 3 and omega 4 to the right side. And since these are scalar stuff, we can solve this in many ways. Like, so here we have 2 unknowns, omega 3 and omega 4, and we have two equations on the top and also on the bottom. So we can solve this in many ways. But I personally like to from this format, change it into this one. So just carefully manipulate this thing to become this manner, and we can use calculator to use to solve this problem. So we have two unknowns. I guess many calculators. I have a video on how to solve this thing using calculator. Maybe I can share that with you. Okay, so but I'm sure you know how to solve this thing using calculator, and you get 8.29. So make sure when you do when you include the omega 2, so that needs to be in radian per second, So your answer basically is going to be in radian per second. But if you want to know how it is in radian per minute, revolution per minute, was- so this one, if you want to convert down to, I guess we have to times by 30 and divide by 5. Okay. If you want to convert from RPM to RPS, you have to times by pi divided by 30. Okay. So, okay, and then for X, you just use this information from, yes, from here. You want to find Vx, we expand this thing, and we differentiate this part with respect to time, and we got this. And then just plug in the numbers, and since omega 3 is known and omega 6 is equal to omega 3, everything in the same body will have the same omega, and uh, so everything is already known, and we get this one, 1550.69 and 920.88 negative for them both. And we can convert it into meter per second by dividing by 100. So this is the scalar value for after taking the root sum square of the components. Then from there, we can also find what is the direction of our velocity x. So that is found to be 211. Okay, so this is the position analysis using graphical method. Graphical method, here I use ordinate to get the position of x. And then graphical solution for velocity. So always start with this known formation, 15.7 meter per second. That's from point B. Then we know this is line perpendicular to R4, and this line is perpendicular to R3. So R4 must always, this line for B4 must always start from the same origin as the first input velocity. Okay, solving that by knowing this intersection, we get our VC and also VCB. And then we can extend that information by these two lines that are perpendicular to R6 and also R7. And we got X over here. So in actuality, if you want to find what is the velocity, absolute velocity of x with respect to the origin. So we have to take this black line, and that is, we will measure that. That is 18.03 meter per second, and direction there, we go in the clockwise direction. So this 149 will be the negative value, negative 149. So if you go in the positive value direction, which is counterclockwise, that will be 211, 211. All right, that's the thing about actuators. So you need to understand what actuators are and how we have to find the number of actuators that will be needed for our machine. So we can use this Kurzbach equation, and it might not tell you to use Kurzbach equation, might just ask you about the number of inputs or number of actuators needed. So, but it is your job to know that you need to use Kurzbach equation in order to answer the number of actuators needed. And then on the issue of what kind of actuator you want to use, so that will probably require you to use this Grashof criterion. So I hope you know how to use this thing, and in the more elaborate set of slides, I think I showed you how some lectures or some notes on how to use this one, with S being the shortest link, L being the longest, and P and Q will be the other two links. So it doesn't matter which one is P, which one is Q. All right, so if you have this kind of problem, so you have to decide when you want to use the Grashof equation criterion, you will focus that on the 4-bar mechanism part, 4-bar mechanism part. So this one is the slider crank part. So that one, do not use the Grashof equation. Okay. All right. Then the issue of how to select motor, this is actually a very important part. Oftentimes, many projects went into failure because they've failed to choose the right motor to run the machine, and actually they can do some calculation and in order to get the right machine. And usually the main thing is to get the top, which is important to, especially during the startup, when you want to start rolling the machine, and that is when the amount of torque is highest usually. And in this example or analysis, I neglect the acceleration, because if this thing is already in motion, they'll probably have certain acceleration, and that needed to be counted into the or considered in that calculation. However, in this discussion, we assume that this thing was initially stopped or not moving, and we want to start moving. So what is the amount of torque that needed to overcome this 1,000 Newton? So this one is moving this way. So this slider over here will be pulling against this 1,000 Newton. So if you use this jet Hochschuler from Valdivia, and you can build this thing. So actually the points, the coordinate, you can get it from using cat. Cat. So this will be all this information. For example, this is 1, 2, 3. So 47, 50. So 3, 47, and 50. So 50 will be the x, and 47 will be the y. It actually comes from this ordinate or coordinate that you can get from your cat. All right, and once you have done that for declaring the points, you can create trust. So trust is basically just connecting from 1 to 2, 2 to 3, then 3 to 4, 1 to 4, okay? And then this one, the fifth one is 3 to 5. So from there, we can get 5 links here. Um, then for material, we are just going to specify 1 and 1. And then for the load, so this one needs to be equal or representing the problem. So that one is 1000 in the positive direction at 5. And in terms of y, there is just 0. And support, which is a constraint. So constraint for the fixed pivot at 1 and 4 will be both x and y. For the slider at 0.5, so we just constrain it so that it will not move in y direction. So we check that over there, or toggle that. And also at the point that where we want to find the forces that will be involved in calculating the torque. So at point 2, you want to constrain in both x and y directions. So when we click on results, we'll calculate the thrust, which is the amount of force inside the link, two-point link or binary link, and also the forces at point 2 over there, which is at the tip of the input link, AB. So that one get this one. And we're going to use that one to calculate the top one. How do we do that? So this is a hand calculation if we do not have access to this one, like in the test. So we are going to calculate from the slider. Slider will be, or the block will be the part, the input part, because we know 1000 Newton is acting here. That will be the point where the system meets with this 1000 Newton force or resistance. And then from there, this 1155 will go into the link 5, link 5 or link CF. And actually, to get this 1155 comes from this one, like the F5 cosine 30. So this is angle is 30. So over here is 30. And can find what this one. So F5 is basically 1000 divided by C 30. Okay, then that should give us this much. All right, and then the second free body, which is on in in link 5. So that will be this one should be in link 4. Okay. This one will be in link 4. And this one will be PC. And then so here we do some calculation. Can do the way that you are used to in statics when you learn that, or you can use this method. Basically, utilize this two-dimensional cross product, and can come out with that F3 is 812. I think in the Valdivia we got 808, 0808. But here I got 812. There is some errors due to the number of decimal places that I choose. Okay, and then all right, and here I use this angle. So F5 is actually pointing this way between C and F, and that should be negative 30, but that can also be from the positive value, that would be 330. So that's why I put 330. It's actually pointing to the same direction. Okay, and then still here, after you have solved for F3, which is this one, you can also solve for FD. Okay, and that FD will be the thrust that will go into link number 4. Okay, and then from there we find that Q delta FD is 107 degrees. And finally, in link 2, between A and B, you can find that this data, so this is the part that's going to be used in calculating or selecting the motor. So we found that T at the top about point A will be about 12,028 centimeter. Okay, and then the force over here in the reaction at the pivot A, so that one would be 696 and for 11 for 18. Okay, and this one is there. Okay, based on the 12,000 meter, so we try to look for a motor that can go beyond 12,028 Newton meter. So this one looks like is a good good candidate for this application. Okay, and I guess one of the topics in this class, especially on my part, is DFMA. We were advised to include this thing, and I have touched this in our class. So DFMA stands for Design for Manufacture and Assembly, and basically combine. There is also a course that I took during graduate work and that was called DFX. So the X can be so many other things. It can be manufacturing, assembly, maintenance, environment. So many other concerns that can be focused, but this one just restrict it to manufacture and also assembly. So the aim is to reduce complexity in the product design, and also simplifies that, in turn simplifies the manufacturing, the fabrication part, and also it contributes to streamline the assembly line. Okay, and when the flow in the assembly line is good, so that will expedite the production, and that leads to greater profit. And overall, it also improves efficiency, and probably it has some good benefits for the workers in the assembly line. Okay, and in manufacturing, they also have this principle or concept called Pokayoki. Some pronounce it Pokayoke, but actually somebody was telling that the correct pronunciation is Pokayoki. It's a Japanese word, and basically is try to avoid errors. Okay, and but overall is trying to make things as simple and as cheap as possible or inexpensive as possible. So if you have different, so all these things can be attached together. So, but this one is using snap fit, plastic bending, riveting, screwing. So all these things will have different production cost to it. The snap fit seems to be the cheapest, but you have to look into whether it solves the problem, whether it's good for the application and things like that. So, and also basically DFMA is known for reducing the number of parts to make it simplified, to make the manufacturing simplified. But as I said in the class, this will make the components or the parts highly customized, and that in certain ways, that will also raise some cost in terms of the parts. But you are in the management, you have to make some evaluation whether the reduction of parts, whether it's worth the investment or not. Okay, because otherwise, probably if you have a spring or a screw, something like that, probably you can use things from off the shelf, ready-made, or things that are produced in mass, which is going to be a lot cheaper, but on the other hand, it's probably going to contribute to the difficulty in the manufacturing or assembly. And yep, that is the give and take that we need to consider in the management. So as usual, the main focus or the main reference is by the book by David Mishka. So if you want more information or more example, you can go find this reference, this book. And I would say that's about it for this lecture or this quick review. Hopefully, I can improve understanding about the lecture from last week, and hopefully it will prepare you for the test. That will be just for question number one, I say. And there's also another part that will come from Mr. Zairo. I wish you all the best. Thank you very much for listening. And I'll see you when I see you, probably during the test. Assalamualaikum. Have a good one.